Okay, maybe we start. It's time. So the course is about square function inequalities, and yesterday I gave a first proof in the sense that I'm going to do it again because it was not completely clear, and also some steps were actually left as an exercise of the bilinear Cordoba-Pfefferman inequality. So let's look at the setting for a second. We have the truncated paraboloid y equals x squared and x less than or equal to 1. Okay? We pick delta, small, and construct the delta square neighborhood of the paraboloid. Okay? In fact, I want to be a little bit more precise. I pick two intervals, J1 and J2, contained in 0, 1, in a -1, 1. Okay? This one. And I consider the neighborhood of the graph of the paraboloid on top of each of these intervals. Okay? Right? So J1 and J2, there's a paraboloid above them, divided it by delta square. Okay? How can I decompose these neighborhoods? I'm going to take a collection of intervals ij for j equals 1 to 2, which are delta intervals, and finite overlap. Okay? Now, for us, it's going to be important to look at the graph of the paraboloid above each of these intervals, I2, and it's this box. And their neighborhoods, which is this box. The box P of ij. If you compute the normal to the paraboloid at the center of the interval I2, you get this vector. It's a vector that points along the direction identified by the center of the paraboloid this way, all right? And yesterday we said that this P of ij is an almost rectangle. Okay, in what directions? In the directions, in the tangential direction of length delta, cross delta square in the normal direction. Okay. And therefore, I'm going to consider a multiplier by P of ij supported on Pij and adapted. Okay. Now, who was here yesterday? I explained what it means and also what it means for the inverse Fourier transform of this guy. Maybe it's inverse, let's say inverse. Okay. Is L1, this guy will be L1 normalized and concentrated on P star of ij. So we're not going to use this part in the proof of the Cordoba-Pfefferman inequality I have on the board, but okay, what does it mean to be L1 normalized and adapted to P star of j? So P star is the dual rectangle to this box. So it's a rectangle that has a long direction of length delta minus 2 in the normal direction, and a shorter direction, still long but shorter, in the tangential direction, and passes through the origin. Okay. So if you tile R2 by copies of this rectangle, this multiplier is essentially constant on each of these copies and decays polynomially, as fast as you want, with respect to the distance from this central P star. Okay. I'm going to repeat this when we use again the spatial localization of these guys, but in this proof, we're not going to use it. So what is important for us is just that phi Pij is supported on Pij and adaptive pool. Okay? And the inequality is now, this is the same as Fpij, yeah? But I don't want to write it the whole time. Okay, let's take the two functions. Let's take a fixed function f, and let's form Fij, Fj, F1 and F2 this way. Okay, so you can think of Fj as the smooth restriction to a function f to this neighborhood. Okay, so F1 is roughly the Fourier restriction to the neighborhood delta square of J1. Okay, because you can choose these multipliers to be almost 1 on each ij, and ij is a cover of jj. Okay, and the inequality is the following: the product of f1 times f2, the 1/2 average, multiplicative average in L4 is controlled by the multiplicative average of the square functions associated to the decompositions I1 and I2. Okay, so this is the L2 norm to the power 1/2.
You assume some distance between J1 and J2?
No, you assume nothing. You assume nothing. No, because these are not, you're not going to use transversality. Okay. In fact, the next remark is that you can take J1 equals J2 equals -1, 1. Okay. And what happens when this happens? I obtain the following inequality for every function if f is supported in frequency on the neighborhood of the whole paraboloid. Okay. And what this inequality is saying in this special case is exactly the classical Cordova-Sachs-Fermat inequality. We said that f1 and f2 is equal to f because f is supported on the delta square neighborhood of the paraboloid, and so it's equal to this decomposition. Okay, what about this side? Well, then you get the intervals I1 and I2 are the same, the collections are the same, and so you get there is no 1/2 because 2, 2. This is equal. Okay, just the same. This 2 is not an exponent. Okay, so this is the classical Cordova-Sachs-Fermat inequality. Okay, I'm gonna prove it. To prove this inequality, we start by computing the fourth power of the left-hand side. Okay. If the fourth power is an integral of f1 f2 squared, because this is the fourth power. Okay, so you square f1, you square f2, multiply everything out, and you're gonna get this sum. I1 and I1 prime, because that comes from squaring f1, fi1 times f I1 conjugate times Fi2 times Fi2 prime. Okay, so just compute the square of this product, or compute the products of the square and distribute the sum. Okay, now I'm going to use Plancherel, and I'm going to transform both pairs here. Okay, I'm not very right. I'm summing over the int, or I have 4 summation indices here. The Fourier transform of this guy is Fi1 transform convolution Fi1 conjugate transform. What about this? The conjugates become exchanged here to make it correct. But it doesn't really, I could ignore it. Okay. Now this is a convolution, and the support of the convolution lies in the algebraic difference of the supports. And recall, where is each Fij supported? In this P of ij. Okay, so the support of the first pair is contained in I1 prime, which is the difference of P of I1 with P of I1 prime. Okay. Remember, this is the consequence, and that's the proof. Now, the trick is to measure how these supports interact. And for this, I'm going to write and prove the lemma. Okay, somehow, the structure of this difference set is making this fourfold sum collapse to a double sum. It's difficult to see it this way, but okay. Let's take 2 intervals different of I1 type and 2 intervals different from it. Okay. I should have said that. Yeah, I said that yesterday, but maybe I'm gonna say it here. We should have assumed that if 2 intervals appear, these are different from 0, and I1 is not I1 prime, then the distance between I1 and I1 prime is greater than 1000 delta. Okay, how do I reduce to that? Well, I'm going to split F1 into 1,000 pieces. I'm going to split F2 into 1,000 pieces, and I'm going to use triangle inequality definitely many times and consider each piece separate. Okay, so the separation assumption is not a problem. You can reduce to that. Okay, now under the separation assumption, let's pick 2 intervals, I1 and I1 prime, I2 and I2 prime. Different. And let's assume that the intersection of I1 prime with I2 prime is not 0. Okay? To have this piece contribute, these two sets have to intersect. Otherwise, the intersection of the support of this with support of this is nil, and the term does not appear. Okay. If then the distance between I1 and I2 is less than or equal than to m delta, and the same for the distance. Okay. This, let's prove this, and then we worry about what it means for us. Okay. Basically, it means that I1 uniquely determines I2, because there cannot be more than one I2 in the 10 delta neighborhood of I1, because I2 are 1,000 delta separated. Okay. This neighborhood is too small. Okay. And same for I2 prime with respect to I1 prime. So the proof is algebraic. There are geometric proofs. Do you know the algebraic proof? So if this intersection is non-empty, remember what this intersection means. It means that there's a point that lies both in the difference of P of I1 and P of I1 prime, and same for I2. Okay, so there exists, so the assumption implies that there exists psi1 in I1, psi1 prime in I1 prime, psi2 in I2, and psi2 prime in I2 prime, with the property that, okay, both the x coordinates psi1 minus psi1 prime has to be equal to psi2 minus psi2 prime, because the x coordinates of the intersection. Okay, and then, okay, maybe this difference, psi1 squared minus psi1 prime squared minus psi2 squared minus psi2 prime squared. This difference is positive and less than 2 delta squared. Okay? Because basically both the points, I mean, it's because of how the neighborhoods are constructed. Okay. The points on the paraboloid are away by less than 2 delta squares if the delta square neighborhoods intersect. Okay, but now I'm gonna call this guy V, and I'm gonna notice. Okay, here it's clear why it's less than 2 delta squared. Why is it positive? Well, it's not positive. If it's not positive, I'm gonna switch this to difference. Okay, but without loss of generality, let's do the proof where this is positive. Otherwise, I'm gonna define W equals minus that. Okay, so okay, but by assumption, this V is large. This V is larger than 1,000 delta. Okay. Why? Well, it's because psi1 and psi1 prime are separated, because I1 and I1 prime are separated. Okay. So now you say that W over V is less than or equal to delta squared over 1,000 delta, which is equal to 1 over 500 delta. Okay, but W, now maybe I erase this. Yeah, now there's a trick. What is W over V? It's psi1 squared minus psi1 prime squared divided by psi1 minus psi2 minus psi 2 squared minus psi1, psi2 prime squared divided by B is both of these guys. Yeah. B is both of these guys. And so what this is, comes up is psi1 plus psi1 prime minus psi2 plus psi2 prime, which is psi1 minus psi2 plus psi1 prime minus psi2 prime, which is twice psi1 minus psi2. Okay. But this is showing that psi1 minus psi2 is less than 1/1000. Okay. In fact, we exaggerated with the. Okay, so psi1 and psi2 are close, and then I1 and I2 are close. Is there any question on this? Okay, so if there are no questions, basically we're done because I'm gonna finish the proof. I'm gonna erase this calculation because it's very easy. Okay. So the consequence is that these have been obtained in the assumption that I1 is different from I1 prime and I2 is different from I2 prime. So in this sum, I have three types of summands, those where that assumption is satisfied. And then I also have the case where I1 is equal to I2 prime, plus the case where I2 is equal to I2 prime. So these summands, I'm not going to estimate them because you need another lemma, which is slightly different, but easier. Okay. But once you turn to those where the pairs are both different, then you're really going to sum over I1 prime only, because there's at most one I2 and one such that this intersection is non-empty, and at most one I2 prime. Okay. So what you get is, by removing the convolution again, Fi1 conjugate, Fi2 of I1, Fi2 prime of I1 prime conjugate. Okay. Now I'm going to apply Cauchy-Schwarz, and maybe I will apply the lemma. I don't need it anymore, to estimate just that term.
What is I2 of I1? Sorry?
Yeah, I2 of I1 is the unique at most interval that is in the decomposition and is at lesser distance than that. Okay, so now this square function is going to become the integral of this summation here I'm going to have the sum over I1 and I1 prime of, this is the point where I can fi1 squared, fi2, and fi1 prime squared, 1/2. And then I have, so here I would have, I would need to write f of I2 of I1, but I don't. And why is that not? Well, each I2 appears at most once by the same reasoning. Therefore, if I write I2 of I1, the sum is dominated by the sum of all pairs I2 and I2 prime. Okay, and I have 1/2. This is the most difficult step, in my opinion, to see that this is equal to the sum over I1 of f I1 squared times, no square root, times sum of I2 f I2 squared. It's because if you square this, you get this sum. Okay, and the square root. So the square of this is this without the square root. Okay, so and this is exactly a right-hand side to the power 2, because that's an L2 norm. So LHS4 is less than or equal than our right-hand side 2. And it's what we have to do. Okay. So the key moment is really 1. And I haven't really used anything. I could have done this with a rough cutoff. Okay. I've only used that the sums of the differences of the supports behave in a nice fashion. Okay. I'm just going to say that you can repeat the same proof for the circle. Okay. The algebra is slightly different because you don't have this nice feature of the paraboloid that W over V is less than that, but the logic is the same. So a similar result holds if you take two disjoint arcs, two different arcs on the circle, you cover each by delta cos delta square cubes, and okay, you keep the same result. Okay, questions? Okay, I think I have time for an application of this inequality. It's a binary restriction estimate that yeah. Let's start by defining the extension operator to P1. What P1? Well, P1 is x such that x is less than or equal to 1 and y is equal to 2. Okay, maybe I should call this P1 truncated paraboloid. So for J subset of -1, 1, I'm going to denote by EJ the extension operator. Yeah, sorry, I should have used Fourier variables for that, but no, I cannot use Y here. Let's use. Range notation. So this is the Fourier extension, and as a distribution, the Fourier transform of this function is supported on the parabola. So the support. Well, okay, this more precisely, the support of EJF transform is contained in this set. Um,
Integral over J.
the integral over J. Yeah. The integral over J. Okay, so the estimate I want to prove is the following. The integral on minus r squared. Okay, let me call this dr. R ball in R2. Centered at the origin, but in fact would be okay for any ball. And the estimate is the following. If you EJ1F where EJ2F squared is less than F L2 of J2 squared F L1 J1 L2 of J1. Okay, whenever the distance between J1 and J2 is much bigger than R2 minus 1. So these are disjoint intervals, they are transversal. Okay. Okay. Why is this a bilinear extension estimate? Because, well, this is basically an L4 estimate for the product of two. This could be written as EJ1F, EJ2F, square root 4. Okay. These intervals are not the same. Huh? They are in fact okay, to use the Cordoba-Pfefferman inequality to deduce such an estimate, we are missing one ingredient. And it's the ingredient where we use the wave packets. Okay, it's this lemma. Suppose that G1 and G2 are any two functions with two port of Gj hat is contained in P of ij for some ij in so we go back to our covering of J2 and J1, which now are disjoint intervals, well separated intervals, and we consider the cover of intervals of length r to the minus 1/2. Okay, so those ij are one instance of the previous decomposition, and r is chosen. I mean, the delta is chosen according to this guy. Okay, so there is some directional almost orthogonality inequality here. And delta. Okay. I am not going to do the wave packet decomposition, of course, but I'm going to cheat. Okay. The thing is, each of the GJ is essentially, I mean, the Fourier transform of GJ of transform is the indicator of P star of IJ with tails. Okay, so the Fourier transform is in PJ, in Pij. GJ is what? Is a sum over all translates of some indicator of P star of Ij translated by K units L2 normalized then WKJ are coefficients, and here there's a decay factor. Okay, with these, each of these coefficients, WKJ is controlled by the L2 norm. Okay. You can really realize this. Okay, this is basically the indicator function of the kth translate of the dual rectangle. Let's ignore all the tails. Okay. And if you have the tails, you just pass an afternoon doing it. It's the same logic. Okay. So GJ is what? Is the L2 norm of GJ times the indicator function of P star Ij over P star of Ij to 1/2. Okay. All of these terms, just keep the first one and be content with it. All right. Why is this decomposition true? It's because we saw it yesterday. The inverse Fourier transform of something that is supported in an almost rectangle is concentrated in the dual P star. Okay. So now we go and look at the proof of the honest proof of. I mean, we from now on, I'm not going to do any other simplifications. Okay, I'm going to erase, no, not this. Okay, now you know the Cordoba Pfefferman inequality. Or maybe I'm just going to finish the proof here. So what is G1? G1, G2 is the L2 norm, no, the L4 norm, 1/2 to the 4th power. Well, it's I compute V1 squared, V2 squared, and then you integrate, you divide by P star I1, P star I2. Okay. And then the key is the intersection, P star of I1, intersection P star of I2. Okay. After this ruthless simplification. But what do we know about this intersection? Well, the normal vectors are y1 is to center of y1 minus 1. And the normal vector of y2 is far away from it. Why? Because these I1 and I2 belong to separated intervals. And so the distance between the normals is of 1. Okay, then I'm going to draw what the intersection is. Remember that this guy is delta inverse. This guy is delta squared. Okay. And so the intersection is, I need a color. The intersection is delta to the power 4. But each of these guys is delta to the power minus 4. And this is, no, sorry, delta to the power minus 2. And each of these guys is delta minus 3. So I have, okay. I have just proved this. And that's what I needed. Well, okay, they are not exactly perpendicular, but they're separated enough so that is approximately this. Okay. Okay.
So here you could quantify the non-transversality, let's say.
Right. You could quantify the non-transversality, but let's say as long this estimate will work as long as delta is much smaller than this. Okay. We can make the estimate. The estimate should depend on this transversality constant, and then it's very easy to. But for us, we are not going to use this. So yeah, the estimate depends on the transversality constant. Okay, so now I'm going to prove the extension inequality. Can I erase? Then I think I can start the proof, maybe finish it in like 10 minutes. Then we do break. Okay. So now I have to erase something. Or let's see. Let's do this. I'm gonna erase this, leave the lemma, start the proof here, and then erase the proof. Now the extension has the Fourier transform, which is a distribution supported on the paraboloid. Okay. So the right thing to do is to pick a function eta, which is greater than 1 on ball BR, and whose support of the Fourier transform is contained in a ball of radius 1 over r. You can do that. Okay, because you can do this for r equals 1. Okay, and then you dilate it. Okay, but I should call this at r, but I don't want to use r sticks. So okay. Then instead of this estimate, we can prove this. Right? I made it bigger. This is now the integral over all r. Okay? But where is the Fourier transform of eta EJ1 supportive? well, this is the Fourier transform. This you can make sense of this in as a convolution rigorously because it's eta is a smooth function, compact support. Okay, this is supported in the neighborhood of it's still there of r minus 1 of J1. Okay, basically, I have taken my measure on the paraboloid and I have made it a smooth function, but now the support is on the r minus 1 neighborhood, right? In this straight. There is something we're going to use later, and I think it's useful to single it out now. What do you think is the L2 norm of this product? Eta J2 J1, say F. Well, if you think about it, this is R times the L2 norm of F on JJ, on J1. Well, why? Well, because you're averaging, I mean, the L2 norm of the Fourier transform of the L2 norm of the extension is the same, right? So if you take, I mean, you need an argument, but what you're doing is you're taking the mass of F and spreading it, okay? And the normalization if this is greater than 1 on BR, this guy will have a certain normalization, okay? This is going to be L1 normalized. And so the L2 norm is R times. Yeah. So this is just basically by averaging. Okay, now there's not much, really not much to do left because we can start from here. And if you think about it, this is basically some F1. So this I can write as the sum over I1 Fi1 squared 1/2, or E J1 F eta I1 squared times sum of I2 E J2 F times eta squared. Okay. So I have applied the covering of the neighborhood of the paraboloid by multipliers. Okay. And now I apply the Cordoba-Pfefferman estimate. Well, I have already applied it. Okay, so now we have the sum over I1 and I2 of the product of E J1 F eta squared times E J2 F, this is I1, E J2 eta I2 squared. Okay, which is this. So we're gonna gain what? We're gonna gain a power of, we're gonna go to sum of I1 and I2 of the L2 norm of E J1 F beta I1 squared times E J2 F beta I2 squared. But we're gaining delta to the power 4, which is R squared. Okay, R to the minus 2. Now you apply Cauchy-Schwarz and that estimate, and you're done. Because, okay. Basically, these R to the minus 2 that you have gained from that estimate cancels each of these two factors. Okay. You first do Cauchy-Schwarz, put together the I1 pieces. This is an orthogonal decomposition, so don't lose anything. And then you apply this inequality. If they want a little bit, stick a little bit of bigger. Because the notation is, I should have done another small line. But this is fine. So let's review it. This is a sum of its ij pieces. This also, so I can apply the Coste-Buffet inequality. And now I have the product of the squares of two square functions. Okay, like this. Because this is in the integral, these two makes these squares. And now, okay, I'm gonna multiply it out and I get to the situation here. And I have something which is along I1, something which is along I2, and I have the L4 norm of the square root of the product, which is this. I apply this inequality, and I turn this into this, but then I can apply Cauchy-Schwarz. And I turn this into R minus 2 sum R minus 2, then I have eta E J1 F squared eta E J2 F squared. And then so the key moment here is the Cordova-Fermi inequality, then you are computing the interaction of transversal wave packets. Then the rest is not. Hopefully I right. 55. So this kind of concludes, the theory of the reverse square functions for quadratic curves in the plane. We're now going to do forward and reverse square functions for directional regions. They are related to this. Maybe it's a good time to take a break. And we resume at 4 or 5. Okay? You're not convinced about this step.
Is this short, but inside it.
Well, it's really this is just the it's
The
too
units of I1.
Direct square function, isn't it?
it's not it's not even for short. You're right. It's expand this out. This is the square of the sum of these squares times the square of the sum of these squares, which is then orthogonality. It's the trick that we used before. It's the sum of I1 squares times the sum of these squares. It's not even, it's equal.
Yeah.
This is equal, and then you have a
Let's do it for k greater than 2.
okay. It's a break, but I will write this step here. Okay, from this this is equal to r to the minus 2 times sum of I1 EJF AJ1F times eta. And then here I have I1 L2 squared times the other thing the same. Okay, and now this is just orthogonality because this is a disjoint. Those operators adapted to Pij are disjointly supported. And now it's
Can you repeat also why is this L2 bound there R?
well,
This eta
it's because you're averaging
is
a certain quantity of L2 mass. What is eta? Hat.
Eta is L1 and L1.
No, eta hat is L1.
Yeah.
Okay, and so
Okay.
eta convolution,
L1 norm constant.
it's
Right.
L1 norm constant, and so,
How do you get R out of this?
well, what is eta hat? Eta hat is essentially 1 over r to the minus, it's L1 normalized, and this interval is long, is r long. But okay, just let's find out what eta is. Okay. Take the convolution. The Fourier, so look, eta is like 1 over BR, right? So eta hat
Yeah, sure.
is like 1 BR
It's a normalized.
B 1 over R over 1 over R squared.
Okay, fine. So you have
Okay, and then
The
the
convolution
convolution you're only losing the L2, it's not really like this. You have to write it out, but if you compute this integral, yeah, just see it on, this is on the Fourier side, not on the spatial side.
yeah, but the convolutions with L1 functions don't give you factors. So maybe there's a trick going on.
No, but this is no, this is a measure.
Exactly. It's a probability measure.
Okay, so the L2 norm, no, okay, it has to be like, okay, there is a lie.
Liar.
I mean, there is a lie that is the lie is this. You have to justify it in a deeper way. But if you do the computations, it follows the averaging idea. The correct thing to say is that this guy is like the Schrodinger propagator. You apply the Schrodinger propagator to it. And x2 is the time variable, and x1 is the space variable. So this okay, this is equal to F L2 of J. By conservation of noise for the Schrodinger propagator. Okay, and then you do the following. Okay, let's do it when everybody's here. Because I know how to do it. It's just that I don't want the lie is better than
There's an extra factor. I mean, on the real line, this is not a one normalized. It's normalized in two variables, and then there's an extra.
yeah. Then you take the supremum. Or,
No, I mean these tricks are very nice. Something to see.
okay. Yeah, let's see it in 5 minutes, 1 minute.
And you want the certificate, no?
Ah, yes.
Yeah.
Yeah, maybe it's a nice idea to show. Just, I mean, in the time, if you take the super, the time variable of the L2 norm is it's the L2 norm of the initial data. Or it's like, and then it's just by basically we integrate one variable away the cutoff. And I thought, you could justify using the L2 norm and moving it by. I mean, it would be R squared, but then you're averaging over the I minus 1 into. So we'll be able to kind of compute it directly.
in the example. Down. Yes. One of this around the goals, actually, you have to be in Falconado in the area. So there's one in the Caribbean, right? That in that street starting from the BDK, and then you just apply. And
they give it to you for a long period?
20 years.
That's
Optimistic.
That's good.
No, I mean, at some point you can also.
Then,
No, bueno, still I don't know, 20, no sé. No, you can transfer to someone. You can
Yeah.
sell it to
Price?
someone. 5.5K
like for the whole period.
for the whole period. You have to pay for the monthly, the maintaining, say, so around 24 euro per month. It's not that much. No, it's not that much.
If you rent every month,
It's around 50 euro each month.
it's more expensive if you rent every month.
Yeah, it's maybe double the 100. So.
And if you want to buy it,
Yeah.
then it will be depends on the area.
Yeah, it depends on the area.
But, yeah. Because
It
it
can be like even
30,000
30,000.
Well, you can live the car in the street, but first of all, you have also to pay for that. You know, it's always better to have your car
No, not if.
not in the street.
Yeah, and also like you might not find a spot and.
Yeah. So.
We have, so, I mean, we have like, our area can find parking.
In Bilbao, it's a problem. I mean, if you're,
Yeah.
if you're outside in some town, it's okay.
Yeah, that's true. You keep the garage, right? For
It's part of the rent of the apartment.
Yeah, that's good.
You haven't moved.
Caravan.
Caravan.
Small things.
Yeah.
Who's this guy?
Yeah, that is. Escaping.
Yeah, so this justification, maybe I should give a full justification of this rectangle, which is not difficult, but requires time. So, thank you. So the function that I chose satisfies this. I'm not gonna prove. Okay, this is not super big. So the norm of this guy, the extension of f dx1 dx2 times eta by whatever you prefer. Well, this is J, yes. J equals J1 or J equals J2 is less than R times the supremum over X, X2. Well, this is true for both coordinates. Okay, and dx. Okay. This is less than supremum over X2 in R of this integral, which is the actual interesting part. Okay, and yeah, the interesting part is that this is equal to the norm of f restricted to J1 square, because the extension Here to norm, this is equal. This is, you can think of this as a time variable in the Schrodinger equation, and this is spatial value. So it's the conservation of mass for the Schrodinger equation that you can just compute by looking at the propagator. Okay. And so it's the economics conservative. These are this thing is just by the definition of eta, what function you're choosing. You can certainly do that. Okay. Okay. So after we set this value to rest, we're going to change a little bit pictures. So I should start drawing the pictures, but in the meantime, I'm going to tell you what the logic is for the rest of today and tomorrow. This portion is out of a paper that has 3 authors in this room, and 2 more have been in BCAM at some point. Has Paul been in BCAM?
As a visitor.
As a visitor. So well, and the idea is to consider square functions in a few of these situations. The first situation, I'm going to take S1. Okay. Well, I don't like this S1. So, I don't know. And I'm going to consider a frequency space. And then the unit disk. And a bunch of sectors in the unit disk where this joint. Okay. So this now suppose let's say that omega j is an interval in S1, and I'm going to define a conical multiplier in the following way. I tell you what the Fourier transform is f hat of psi times beta j of psi, where beta j is smooth and supported on omega. Okay. Here's another one. So the square function you consider here is the following. You assume you have n disjoint intervals C, and you ask yourself if this is a bounded operator in P. In general, we will see why the constant in a little bit why the constants must depend on n. For what regions? For what ranges? Okay. That's one of the square functions I'm going to consider. Here's another one. Because actually, the one I should have written right away is this one. Take S1 again, take the delta square neighborhood of it. And cover it as before. We've done it for the paraboloid with almost rectangles of thickness delta squared and tangential length delta. So this is the same. I'm gonna call this P Pj. It's an almost rectangle. In direction Vj perp. Okay, where Vj is the normal of size delta. And so this is essentially the same estimate that we had before, but it's the other direction. And here it should be kappa delta. There is yet another situation, which is the following. Let V1, Vn be n directions, any n directions in S1. And for each of these, take a collection of boxes of arbitrary eccentricity pointing along Vj. Okay, but now you also have another direction in the picture, and maybe this. In the same coordinates, but longer, you have this. Okay. And these are all almost rectangles. So there is one almost rectangle. This is Pj1, Pj2, Pjk. You don't know how many you have. Pj plus 1, 1, Pj plus 1, 2. And for it, you consider the smooth square function. Sum over j equals 1 to n, sum over k, f p jk. Okay, these situations can be put in the same framework. Okay, this is essentially a Rubio differential type square function. In what sense? For each fixed j, you have a disjoint collection of rectangles of arbitrary eccentricity, for which we know that the Rubio differential estimate holds. Okay. Now, you have n direction. Altogether, the collection of frequency supports is still disjoint, but you have that they can be in whatever of the n coordinate systems you allow. Okay. So, by the way, in two of these instances, it is clear what are the almost rectangles we talk about. Okay. What about the cones? These are not almost rectangles. So what I'm going to do here is to consider another square function that you obtain by subdividing all these cones into little pages. Okay? Okay, now each J cone is also decomposed into a union of little pieces, and I'm gonna denote by PJK. And it's the intersection of the cone omega J with the little Pelli annulus to the K. Okay, maybe I should write what, now I'm going to write the square function. So if omega J is the cone and LPK is the case little Pelli annulus. Okay, and PJK is omega J intersection LPK. Then I have yet another square function, right? Which is this one. Somewhere J equals 1 to n because I have n cones, somewhere all K in Z of F PJK squared. The constant here will not depend on little Paley, it will only depend on n. Okay, actually, so there are now 4 square functions. 4, 1, 3, and 2. Okay. We can forget. We kind of can forget about 1 because bounds for imply bounds for 1 by vector valued little Pelli theory. Okay. If you want, I can show you the implication. It's not so good. Okay. So I put some Kn here. And I told you, I anticipated you that there are going to be some restrictions on the range. For instance, this is a Rubin differential type square function, so we know that we can assume we're going to restrict ourselves to values of p that are between 2 and infinity, otherwise it's not going to happen. This is stronger than a Rubin differential. Okay. Now we will show that even in the most optimistic range, which is p between 2 and 4, this constant must depend on n. And of course, you can make it depend on n in a trivial way for p greater than 4 by using triangle inequality and bounds for the single cone multipliers. That's not a problem. But we are not interested in those trivial bounds. So we're only interested in these bounds in the non-trivial range where we expect logarithmic behavior. Okay. I mean, the polynomial bounds are trivial, so we don't insist on them. And I'm going to give a counterexample in this range, and the counterexample is easier in the other range. Okay, so the unit, now maybe I'm going to erase as I go, but the unit here is lower bounds. Lower bounds are usually quite interesting because people don't spend, I mean, these are even more interesting because the Kakeya set appears in this lower bound. Okay. So lower bounds, I'm going to give the lower bounds for the hardest case, which is 1. The other ones are similar. Okay. So the trick is, let's consider one of the cone multipliers. Okay, I call them a single C omega J. It's a smooth cutoff to this cone. Okay. Actually, we said it's compactly supported in the cone, so maybe. Okay. Let me be a bit more in the case. Yeah. Let me follow the notes because otherwise it's. Well, the idea is that, let me first give you the idea. Suppose that this direction is, the central direction of the cone is okay, this is a smooth cone. There is also the rough cone, which is the region bordered by these two directions. I'm going to call Wj and Wj plus 1 for reasons that I'm going to explain. Okay. So this is the smooth cutoff, and then we can consider the rough cutoff. Okay. This guy is the difference between two Hilbert transforms. In direction Vj, which is Wj per, and in direction Vj plus 1, which is Wj plus 1 per. Okay. Well, I have lied a little bit, but let's this two-sheeted cone is basically the difference between these two multipliers. Okay, so I don't know. I'm gonna call this C. This is the multiplier CWJ. Okay. I have the argument written down, but CWJ is an average of small rotation of the rough. Okay, I'm not gonna write the formula because you don't really need it. Okay, so the point is lower bounds for the smooth will follow from lower bounds for the rough. Okay, once we establish them. Okay, so I can just prove lower bounds for the rough restriction to this, the square function of the rough restrictions to this cons. But this is a directional singular integral, okay? Because it's the difference between if HVF is the directional Hilbert transform, I'm confused. I'm confused by the sheer quantity of things that are moving. Okay, what I want to say is this multiplier is up to identity, the Hilbert transform in direction B, up to summing and dividing by 2. Okay, so in the end, instead of considering these rough operators, we can consider the difference to Hilbert transform. Recalling that the directional Hilbert transform is really an integral along the direction. This is f of x plus tv dp. And here I'm going to put principal values. Okay, so instead of proving lower bounds for the function of smooth cones, I can prove it for so I have reduced. Now I will need all of this. I have reduced to the lower bound sum over j equals 1 to n hvj minus h hvj plus 1 f half p greater or equal kn f. Okay, so this could have been said in 2 words. From the smooth cones, you pass to rough cones. From the rough cones, you pass to the difference between 2 consecutive Hilbert transforms. Okay. So the f for the counterexample is the KSF. Now, suppose that the 2 consecutive directions are e to the 2 pi I j over n. Okay. The counterexample does not always work, but until now, this reduction was fine for any set of directions that I label consecutively. Okay. And then, well, for all n, there exists a set E, which is a union of rectangles, j equals 1 to n, Rj, each with the properties Rj is a 1 by 1 over n rectangle along Vj. Okay. The measure of E is less than 1 over log n. Okay. And if I translate Rj by 3 units along Vj. This is our phase-wise disjoint. Okay, so I'm gonna make a sketch. This is R1. It points along B1. Then I'm gonna draw R2. It points along B2. And the reach, this is R2 tilde, and these are one tilde. Okay. So in particular, from the last condition and the shape, it follows that the union of the R tilde, I'm gonna call E tilde, has measure roughly one. Right? Because you make them pairwise disjoint, so there's okay. And now if F is 1E, if F is 1E, what happens? I'm gonna do it later. But now let's compute this guy. I fix K, and I'm gonna compute what on RK tilde this sum. Apply to 1E. Okay. What happens is you are a point in this guy. What do you see when you apply HVJ minus HVJ plus 1? Okay. Well, if HV1 is integrating along this line. So, okay, you get HV1, 1E. And then all the other ones are 0. Because of the separation. Okay. The picture could be misleading because, you know, I have translated just by a little bit. If you translate by a lot, then you see that with V2, you hit no rectangles. Okay. So all of this reduces to HV1, 1E. Okay, and HV1, 1E is roughly 1. By the way. Actually, even better. This is HV1, 1 at 1. K is 1. Okay, the other rectangles are not seen. Okay, so now we can get the lower bound. Okay, the measure of V tilde is roughly 1. But then, this is basically the integral over each RK tilde of HVK 1 at K. Okay? So this is like 1 at 1 tilde. Okay, but now I'm gonna use this equality. Okay, I have to sum here. I have to sum over k. Okay, on each piece of E tilde, I'm gonna write 1 in this way. Okay, so this is the integral of 1 E tilde, and then I'm gonna use this equality. Okay. So finally, this is the thing I'm trying to obtain a square function of. No, this is 1rj, not 1e. Ah, yeah. Yeah, it is. For the same reason, you get on arcade, you just see, yeah. This is just by using the directional nature. Okay, this is the, I don't know why I have the notes and I don't use them. Okay. Just look at this picture. On R1 tilde, the only thing that contributes is R1. The other thing is everything needs to, I mean, is carried out in directions that do not touch R1 tilde. Okay. So, okay, and now I'm gonna use a square function bound. Because I can pass this sum. I'm gonna use the then h vj minus h vj plus 1 applied to 1e. Okay, what about this step? If I have this equality, then this is set dual with some Fourier multiplier. I can bring it on this side. Okay, now this is bounded by the square function of the rectangles 1rj squared to 1/2 in LP prime times the constant I'm seeking for, because I do the square function of this guy. Let me call this TVJ. TJ. TJ 1e squared. 1/2. Okay. I applied the square function bound now. And what is this? This is Kn P E tilde. E tilde is 1. And then 1rj squared 1/2 P prime, which is greater than log n, the 1 over log n. to the power 1/2 minus 1 over 3 prime. Okay. This is not no, okay. Let's.
You need another trick.
Uh,
Because you get the overlap, right?
Yeah, you get the overlap, but
Can estimate the overlap. But this somehow separate estimate.
but okay, this is actually log n to the 1 over p prime minus 1/2. Okay, this.
That should be E there. Right?
No, e tilde. E tilde here. It's not e tilde. This is 1 and 1, it cancels out. And then
You apply the operator to E and
to e tilde.
to E. E is the Cajelia, right?
E tilde is the reach. I got it.
Exactly.
So I got it on the reach, the operator.
Okay.
Okay, maybe I have the wrong proof. Because yeah, it was easier the other way. Okay, if you have no, then I have to redo it again. Okay. Forget about the last part because maybe this also works, but it's easier to do it a different way. Okay, let's review this part. This holds, right? Let's check. If I am on R1 and I apply all of these operators to E, all that I get is 1 over R is this. Okay. Well then, let's redo this guy again. Yeah, I don't know why I did it the other way. This is sum of the integral of the indicator function of R1 tilde. Okay, but now this is, I'm going to use this equality. This is 1 R1 tilde. I don't need to pass the operator. I don't know. J equals 1 to n, Tj 1e, where Tj is now this guy. Yeah, I don't need to, now it's easier. Okay. Well, now you have to believe this. How do I get the square function here? I mean, yeah, okay, but this is J. But this cannot be the same J, so let's make it K. Now it's Well, Cauchy-Schwarz, but this is not going to work because this I have two summations here. Okay. Okay. I have to look at the paper. The other lower bounds was much.
Just do it for the squares. I don't see the problem. You just do it. I mean the square.
But
Yeah, directly. I mean, your estimate is point-wise.
okay.
Like take one conical multiplier.
Then it's written
apply it to some function.
funnily in the paper. Because it's so. No, you have to do. Need some years, but I looked at it and this one's by far the hardest. So. Very good. Absolutely. Okay. Well, this is the union. Let's just write the union here. So union of R K tilde J. Okay. And now I will do we skipped a billion steps and I don't think this is correct. There's a tilde in the paper that is missing, that's why. Okay, this is bounded by the square function of Tj one e squared, okay, 1/2 times the square function of 1 of j tilde. Okay, and now you apply, this is just 1, the norm of this guy. So you give the LP prime norm to this. So in the end, you are going to understand that this is less than Kn times E to the power 1/2. And then you don't get it. I mean, so. I think it rests on, it was correct before, and it rests on the fact that this square function is bounded by it's because, okay, this is bounded. So it was correct before. We have to redo it again. It's an estimate on the overlap of the cubes. So you need that. I don't know why I lost confidence in myself. Okay. what we did correctly was to reduce to this by passing to the adjoint. It became the sum from j equals 1 to n of pj, 1 e tilde, and then 1 rj. Because what you need is this estimate. And if you have that, you create 1 e tilde using this sum, and then this is not difficult. So we don't need to redo all of it. And now I'm gonna write this as less than or equal, then, well, this is less than or equal, the integral from j equals 1 to n of tj 1 e tilde squared 1/2. And then here is the not so nice, but you have to handle it in some way. So we will. Okay, now I do holder, and I obtain my bound kn e tilde. But now you have to estimate this guy, sum of 1 rj. We don't need to keep the squares, of course, but it's 1/2. And then this is p prime. Okay. So let's look at what this norm is. This is the sum of is the L 1 rj p prime over 2 1/2. Okay, the Kakeya, the estimate we need to use an estimate for the Kakeya maximal function, or the fact that this is, I mean, that's set. And you're gonna have this is log n to the power 1/2 minus 1 over p prime. Okay. It's because you can either compute it directly or use a certain estimate for the maximal function. Okay, now so this tells me that Kn is less than or equal, is greater or equal than log n to the 1 over p prime minus 1/2. Okay, so this is the lower bound, and now I explain to you why that is. Means a few years, so I sort of overlooked that detail. So in general, if you have the maximal function Mn, which is supremum over all tubes, 1 cross 1 tubes in 1 over n separated directions. This is the so-called Nigodi maximal function that we already saw yesterday. Okay. Now, by taking the adjoint, This is bounded by Mn. Let's do it for a Q. Q prime. Okay. And if Q prime is greater than 2, this is bounded by log n to the 1/2, well, to the 1 over Q prime. Okay. So now if Q is equal to P prime over 2, then Q prime is equal to 1 minus 2 over well, 1 over Q prime is equal to 1 minus Q prime. Okay. And so 1 over, and that's now why this has to hold is because you can show that this quantity is actually comparable over a generic set of rectangles is comparable to this norm by taking the adjoint operator. DQ prime maximum function. Okay. So I think this settles it. But you really need all of this. So it's the most difficult counterexample in the paper, and the others are simpler because you don't need to handle the square function this way back to this guy. Did you remember this?
If I don't look it up.
We wrote it. So I just said you or me because it was already in the first section of the paper. We wrote by ourselves. Okay, so let me finish just with a quick remark. The counterexample is relevant for the range 2P4. And so one big question is, okay, can you prove sharp bounds at the endpoints P equals 2, of course, and P equals 4? P equals 4, this guy is 3/4 minus 1/2 is 1/4. Funny thing is that this is equal also to log n to 1/2 minus 1 over 3. It's nice. Okay, sorry for the. But we've done a lot of things today. So we have done this counterexample, restriction, Cordoba reference, or I tell you that the break